Did you get my essay last term?
Maybe resend it to me if I didn't hand it back to you.
Okay, because I put it in your box last term.
Yeah, I mean, I could have just like lost it now in the shuffle. So just if you could just resend it,
Okay.
then I'll get it back to you.
Actually, I also have a question about that. So I never ended up getting in the rough draft, so should I give that to you first, or should I just go ahead and go with the final draft?
It's up to you. Like, so if you have something and you want to show me a rough draft, I think that would help you.
Okay.
So, but yeah, otherwise just go for the final.
Okay.
All right, let's do some announcements. So just a reminder, we're going to do our one pot lab this week. So kind of rearranging the schedule just a little bit so it may not match that great either, because one pot lab is more about coordination compounds, but that's okay. I chose it because if you remember, so this is more for the Thursday lab people. We're going to have people that want to do a photo shoot. So that's just the, on-campus marketing people. They want to get some action shots in the lab. So just keep that in mind, that you might want to look cute on Thursday, or otherwise, right, let them know that you don't want to participate or be in the photos. So just keep that in mind, right, either way. So either look cute or plan on, telling them to please leave me out. And so other announcements. So I'm still kind of working on the field trip that kind of, so let's see where we're at. So I'm pulling up our syllabus. Let's see, did I fix your syllabus? So I did not, I haven't fixed your syllabus, so obviously we're doing the one pot this week. Week 7, we'll go back and do that radioactivity lab. Like I said, I didn't think it'd be that exciting for them to take pictures of us staring at the computer while the thing beeps. And then the next week, we'll probably move up the aspirin synthesis. And so tentatively, I'm trying to do like maybe an optional field trip week 9 then, but we'll see. And it's going to have to be optional at this point because of policies and procedures. We're just like running out of time, so it can't be an official trip, but maybe we can do something unofficially with extra credit. And so also thinking, because I think that leaves us with a blank week. And so actually we might want to do the field trip. So what I was kind of thinking, so we have our presentations on week 10, which we'll leave. I was kind of thinking week 9, maybe we could do an ice cream making lab, so we could like compete and do like the rock salt method of making ice cream versus liquid nitrogen. And of course we could eat the ice cream and maybe that would be fun. And so going back to that, so the field trip that I'm trying to plan now, or the optional trip, would be out to the Rogue Creamery, like out in Grants Pass where they have their dairy place. I don't know if anybody's been out there. So trying to set that up. I don't want to make promises because everything is like falling through. I'm just trying to get the manager to like call me back and see what kind of deals they would work out for us. But I was thinking maybe if we went week 8 on the Friday, again, I'm just kind of throwing out ideas, then we could make ice cream on week 9 with potentially a little bit of their melt. Again, just maybe, just things to kind of think about, but we'll see what happens. So that's where your field trip / other lab is at. And so I posted this finally on Blackboard. So we want to think about week 10, our poster. And so like I mentioned, right, we're not going to have a lab practicum this time, but we'll just do a research presentation. And I don't know if you guys want physical copies of the research paper guidelines. They're pretty similar to the previous one. And so just kind of the idea, and again, right, check the feedback on your paper or meet with me if you don't understand my scribbles or you need more guidelines for my scribbles. Like I'm happy to meet because I'm not married, right, to this whole just like, oh, it has to be introduction and then describing the research, right? You just want to make sure, does it kind of flow? Are you presenting your argument, right? Does it make sense? And so a lot of you did kind of set it up this way, but I think the main criticism I had of people's paper is like almost too much describing the research methods and then not enough just getting into the results or like showing charts. And charts and stuff is what we want to think about too for our poster. Oops. And so I have on Blackboard, so this is kind of just like a general poster rubric, right, that you want to have nice, obviously cover the topic, kind of bullet points. So now you want to translate your paper to a poster. And then graphics, so obviously you want pictures. I kind of try to put in your paper like what good structure suggestions would be, or maybe good charts to show. And then organization and layout, so that kind of goes together, just making sure everything's, titled and flows and looks pretty. And then obviously sources, and then you'll be, graded on presentation. but it should be a pretty friendly experience. And then I also posted sample posters. Where are they? Where did I put them? So it's under poster requirements. And so there's a few template links, potentially. You can also, so I posted back when we first did this. So this is, now you know the secret of Dr. Murphy. So Dr. Murphy, our wonderful math professor, is really a computational chemist by training. So this is his poster, one of his research posters. So you can see how a very math-heavy paper is presented. Obviously, bullet points, right? Nice charts here. So some of you that have kind of more technical papers, I would expect, you know, charts, data, numbers, something. And then, of course, you can talk about the chart. And then, again, you can see how it's organized, bullet points. And then I also put one of my examples on there. So this is an old ACS poster, and you should be able to download it. And since it's a PowerPoint file, you can edit it and use this as your template. And so this is just kind of a standard synthesis chemistry paper, an introduction, you know, some reactions, what are you doing, maybe what happened. So obviously I was showing a lot of different reactions in this case and crystal structures. But again, depending on your paper, right, you should have figures, schemes, a lot of drugs maybe, so you can have like different drugs and maybe next to it the results, and then somewhere references, and then any other conclusions. Yeah.
So will they all be like digital posters?
So I would like you, so it depends. I would prefer that you print them. So yeah, I want them printed. So right, these are obviously digital, but like I said, you can download mine. And then for printing, so I've asked in the past, and they haven't ever supported funding us printing even at like Kinko's. So if you like, I think there's a way to print like from PowerPoint from like one big poster makes many slides. So I can like help you with that, but that's kind of the cheapest option. And if you want us to like print it, we can do that at school. So at the very least, I can print it out in color for you guys for your poster. And on paper, that's about all I can offer. Unfortunately, I couldn't get the budget support for, again, Kinko's. And then if you wanted to, obviously, like spend your money, you know, that's your own choice. I'm definitely not expecting you to do that. And then there's also, I don't know, you probably have noticed that other like research poster hanging up in HEC 312, like over the fish tanks. So that's another, so you can look at it this week if you're in lab, but that's another, you know, good research example. And that's like an undergrad level poster, so, you know, it's kind of like more friendly. There's pictures and obviously some data. But hopefully that gives you a few ideas. And then, like I said, if you need help printing, I can definitely try to offer color printing services. And then, like I said, I would like to meet on Thursday as a class. I don't know if everyone can do that. We can double check that closer to the week. I don't know if that works for the Tuesday people. Yeah, just so we can have a nice big poster session. Otherwise, I would hate to make people do it like individually in front of the class. I know some people have presentation anxiety, and I'm trying to do it more like poster format, kind of casual setting, because that's, like I've mentioned, how some of those research conferences work, right? There's two different types of presentation. You have your poster presentation where you just kind of stand there. It's very casual and people can walk up to you, ask you questions, but it's not really a formal talk. And then obviously a conference will have the bigger speakers and the formal talks where you do give a PowerPoint, and that's usually like a big deal too, though. All right, any questions on the poster or paper? So I know I owe at least one person a paper I forgot. So again, email me if your paper did not make it back to you. So, or if you want updated, you know, hey, here's my new draft. Happy to help. Or we can meet, like I said, especially if you don't understand my scribbles. Okay. Questions? Any other announcements? Oh, and I'm still grading your midterm. I think I forgot to say that. So I'm like in the middle of grading it, hopefully by Thursday, but we'll see. All right, so let's dive into chapter 25. I still need to post the notes online. And so some of this I think we covered accidentally on week 4, kind of before the midterm, but we'll go over it again and kind of make sure we're all on the same page. And so we start off with kind of the history here. So Volta was kind of the first one to try to make a battery. So this was in the 1800s, and they literally just piled up like copper and zinc metal, and then in between, so you can't really appreciate it in the picture, but I think there's either little bits of fabric, or at least they soaked it in some sort of electrolyte solution. Not sure what that was, but at the very least, right, some salt-containing solution. And so yes, right, that Volta was able to generate some electrical current from that. So that started off the first battery. And I mean, in some ways, battery technology has not changed that much. And so now we have, of course, how do we measure how much voltage is going through? And so voltage, again, like we kind of touched on previously, so we have to have our voltage, and this can essentially, right, push our electrons or make a non-spontaneous reaction occur, right? So we kind of saw that with our electrolysis lab. And then we just have that our electrical energy is defined as our volts multiplied by our charge. And so we want to think about this in terms of joules. So 1 joule is 1 volt times 1 coulomb, and then 1 amp is 1 coulomb per second. And we have our I, so right, I is current. And so then, right, our charge is our current then times our time. So, and then other things to know. Okay, so we have symbols here. So right, charge, Z, voltage. Again, that's energy over our charge, current, total charge over time. And then we also want to know what 1 electron is. So we have 1 electron is equal to 1.602 times 10 to the negative 19 coulombs. So remember, that's just the fundamental charge of the electron, so that was found by Millikan. And then Faraday's constant, which will help us as well. So now Faraday's constant gives us our molar quantity, and so now we have 69,485 coulombs for 1 mole of an electron. So you can see, right, you multiply your electron by your mole quantity, so that gives you Faraday's constant. So both of these could be helpful. All right, so now let's look at a typical question. And so again, right, we'll look at our units here. So charge is given in coulombs, right? A volt is a joule per coulomb. And then our amp is our coulomb per second, right? So this is giving us our rate of flow. And so now let's look at a sample problem. So now we have a current of 1.5 amps, flows for 5 minutes. What is the quantity of the charge?
The answer is 7.5.
That's not what I got, but what did you do? Because maybe you just forgot to multiply by something.
I used the z equals I t.
So we got charge, except, so we want to get our total charge, right? So we need to multiply it. Yeah, so we have I equals z over t.
That's what I didn't solve for I.
Or, yeah, so, because we have to solve for z, actually, the total charge. So our total coulombic. So yeah, it ends up being that it's our current times our t. So then we have our current of 1.5 amps.
So would you time me in seconds?
Yeah, so that's the other catch. So that's what I was thinking that maybe you hadn't done. Because, yeah, looking at our units, it's per seconds. So exactly, so we have to multiply by seconds. So, of course, it's times 5 minutes, and then converting minutes to seconds. And so now, oops, let me get my calculator fired up while y'all tell me what you got. And so it looks like people got this now, 450 coulombs then. So we'll do some more problems with this later, but just kind of a hint, right? At some point, we'll be able to quantify how much we can plate out, essentially. We'll just have to keep in mind, right, again, our number of electrons. So that's where, you know, whether it's 2 electrons, 1 electrons, that will matter when we're trying to calculate how much charge we need. But like I said, we'll do some example problems, but just kind of so that's on your brain. All right, so then this is kind of a little bit of a repeat from 24. So I think we kind of covered this, but like I said, we'll still go over it. So again, like we were saying, now we're trying to study these redox reactions that either produce an electric current. So we said if they produce one, they're spontaneous, at least in that direction. And then we saw those that require an electrical current. So those would technically be non-spontaneous. So we saw, right, like water splitting, so that obviously requires voltage input, and you don't have water just splitting normally. And then, well, we didn't construct a voltaic cell, but that's something that we could do for fun if we got bored too, week 9. But thinking about how a battery is constructed, so converting our chemical energy into electrical energy. So obviously that's an electrochemical cell or battery. And so again, like I kind of mentioned, battery technology really hasn't changed too much from this. Obviously, right, they're just kind of researching new materials. They have those lithium batteries, which are really lithium intercalated with like oxides to try to make it less dangerous, but obviously still flammable. And then there's lots of research in like organic batteries to, again, try to do this, but still fundamentally, right, redox reactions driving it. And so like we mentioned, these spontaneous redox reactions are formerly known as a voltaic cell, or again, galvanic cell, which is just our battery. And then we saw non-spontaneous redox reactions can, of course, be made to occur by the addition of electrical energy, or again, recharging a battery. So that's, again, the idea for these rechargeable batteries, that you have reactions that go back and forth. And usually you don't want them to undergo side reactions, so it's the side reactions and the impurities that obviously kill your battery life over time. And that's where, you know, they try to minimize those side reactions by having like the controlled slow charging thing, or at least so they say, right? There's all these tricks for battery life.
Is that why they like tell you not to let your phone get too hot on the charger and stuff like that?
Yeah, so that's kind of the idea, that like if it's getting too hot or charging too fast, like that could lead to bad like side reactions, but you know. So that's all back to battery technology research, so that like, yes, they can charge faster and more efficiently, but anyways, electrochemistry is cool. There's just a lot to it. And so again, we looked at this reaction, so just kind of a reminder. So we performed this before. So we have the copper 2 in solution with our zinc strip, and we all remember how then, right, the blue turns colorless, and then the copper rusts, in quotes, as it does this reaction. So again, spontaneous reaction. And like we maybe remember, the whole point of the galvanic cell was then to separate these two reactions and have them occur again from a wire. So blah, blah, blah. So again, some points that we made. So electrical current, this is something we didn't do in 24, so we're going to do that like I mentioned now. So we're going to be quantifying the electrical current that can be generated. Again, paying attention to how many electrons are flowing. And so again, like we had mentioned, our redox reactions are driving this. And again, redox reactions obviously involve the transfer of electrons. And spontaneous reaction obviously does not require external energy. And again, just a reminder that our delta G is negative for spontaneous reaction. And again, obviously, this is what makes your battery turn on. And so it mentions, right, to use this current, we have to separate where the oxidation is occurring from the reduction. Again, right, we're not going to get a battery if we stick these two things together. We're just going to get a disintegrated copper piece, and that will not work. And so, like I said, we went over this, but just a reminder. So we have our oxidation and reduction reactions in our separate half cells. And so if you remember, right, we had our diagram then. So again, just to kind of emphasize everything, we have our metal and then our corresponding solution. And so they picked nitrate, right? Obviously, nitrates are always soluble, so people tend to use them, but we could have picked chlorides or whatever in this case, as long as it's soluble. Same thing with the copper. So again, we have our copper cathode. They picked nitrite. Again, nitrates are just highly soluble, but a chloride sulfate, would have worked just as well. And so again, right, we have to have our circuit. So just like we saw with electrolysis, same concept. Just instead of a battery hooked up here, we could hook up an LED or again a voltmeter and measure it. And we have, so our anode. So anode is always where our oxidation occurs. And again, they both start with vowels. So A and O, and they're both kind of round vowels. So anode oxidation, and then positive end of the battery in the electrolytic cell. And then compared to the cathode, so cathode is always where reduction occurs. And then cations are attracted to it. And so again, we can see our anode, so our zinc, right, donating electrons, so it's going to be losing mass. And then those electrons are obviously flowing from the anode to the cathode. And then again, right, reducing the cathode there and plating more copper on. So the nice little diagram of plating copper. And then again, don't forget about the salt bridge. So it doesn't matter too much what it has, just as long as there's some sort of ions flowing. Sodium chloride soaked cloth would work just fine. All right, so then we had looked at our voltage in our cells at least. So right, we had calculated our potential. So again, just a quick reminder. So the voltage is our difference in potential energy between our reactants and products. And so then 1 volt is 1 joule of energy per coulomb. And so then we can calculate, right, for non-spontaneous reaction, how much force we have to essentially push through. And so again, right, the current, we saw that on the previous page, so that's just measuring our flow of electrons. And then 1 amp of current is 1 coulomb of charge flowing per second. And so 1 amp is equal to 6.242 electrons per second. So again, just another conversion. And then electrode surface also dictates the number of electrons that can flow. And larger batteries tend to produce larger currents. And of course, these larger batteries can also just be more little batteries just hooked up in series to get you a larger voltage. So it just depends. So just kind of think about that as well. Yeah, like a 9-volt battery is actually just a bunch of little AA's in series. I don't know if people knew that. All right, so we looked at our cell potential, or at least we started to. And so we'll look at a few, like I said, special case conditions now in this chapter. And so we had gotten an introduction to it. And so again, I like to write our reactions properly in the correct orientation, right? Change the sign from your reduction chart, and then we can calculate our cell potential. And our cell potential also just tells us, right, the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. So again, right, that's what your electrolysis lab was kind of showing you, is like which one has the lower voltage, which one is going to happen first. So I'll add that to which. And so I kind of mentioned this during lab, but it's good to kind of talk about it again because this is a big deal when you're trying to do electrochemistry and like design a new material. And so we mentioned, right, that we have the competing reactions of water, so the electrolysis of water is always a problem. And so that's something to think about, right? Even if you create this new wonderful material, if you're competing with water, well, that might not be so great, or any other solvent. So that's something that chemists have data for, is like in different solvents, right? What's the reduction potential of these compounds as well? So it's always something that you have to keep in mind. And so when we were looking at these cell potentials here, so they're just our standard cell potentials. So again, that's 25 degrees Celsius, 1 atm if we have gases involved. But really, the important part is the 1 molar concentration of solution. So later in this chapter, we'll figure out how to deal with non-standard concentrations. And so do you remember how to calculate then our cell potential for this? So we did it, like I said, before the midterm. So what do we have to look up? What do we do? And should have, so maybe you should have your chart, your notes, your reduction potential chart will be handy again. So how do we figure out our cell potential? And so what do we remember about, there's a few different ways to do it. I think there's some formal formulas, but what do we say was kind of the easiest thing to do? And we have our reactions here written to help us. So what should we look up at our chart? Remind me. Yeah, so we need our reduction potentials, so let's look up, if I can find zinc. So zinc 2 plus, and then what do we say about the signs and all this?
Stronger the oxidizing agent, the weaker it's going to be at reducing.
So that's also true. So we have, right, stronger reducing, weaker oxidizing. But what do we say about like when calculating the potentials and for writing them? Right, because this is our redox potential of our zinc 2 plus 2 electrons. But then what's going on in our,
The zinc and the electrons are on the same side, so we flip the sign.
yeah, so let's do that, right? So we want to write it just how it's reflected in our battery. And so exactly right, flip the sign, that's the important part. And so I'm just going to rewrite this now on this other page. So basically the equation they have here, right, since again zinc is acting as our anode, so it's our reducing agent supplying our electrons, and then yes, flip our sign, so positive 76 volts, and then we can do the same for copper, except copper's probably already in the correct direction. Let me pick, there it is, sorry. Copper 2 plus 2 electrons, so make sure we pick the correct process. So plus 0.34 volts. So again, right, that was already the direction it was written. And then now we can just add them together. And we should get 1.10 volts there. And then the other thing we went over, but again, we're going to continue practicing it in this chapter. So you'll be tested over it obviously later, is then just kind of making our shorthand cell diagram, which if we remember what that was, so that's, I'll just set it up generally, right? So we had our oxidation anode, and then those little lines, then our reduction anode, or cathode, excuse me. So then for our zinc copper cell, we have zinc, and remember we put the metals on the outside, single line, and then you can put either zinc 2 plus at the very least, or you could of course write out the full compound. I just want to emphasize, right, that the nitrate doesn't matter. It doesn't have a significance. It's the zinc 2 plus. And then again, our indicating a separate cell. And now our reduction cathode. So copper 2 plus. Again, you could go ahead and write the exact compound if you wanted to specify. And then copper solid.
And so this is just kind of like the image of what it would look like inside of the battery.
Yeah, so the idea is like this is a cell then of a battery, and so right, that translates either to the cell of a beaker, or if I want to draw a horrible crude drawing of a battery, the inside is like kind of one cell, and then there's like a little film membrane, and then the outer part of the battery is the second cell.
And so the 1.10 volts, that's the overall
Yeah, so once you added up your anode and your cathode, correct, that's your overall cell potential. So yeah, that's your battery rating then. And then you can imagine, right, so you could take two of these little beakers, right, hook them up in series, and then now you're at 2.20 volts, right? So then you just keep adding them, which is essentially all batteries are, is like these little cells, just in, obviously the batteries are more like pasty forms of these compounds kind of intercalated in different materials to make them more battery, obviously in the battery. And yeah, so again, the shorthand just kind of shows us how to build our battery really quickly. So that's part of your homework too, just like translating this little battery notation to a cell. And so this is a good reminder that sometimes we might have reactions, right, that do not have just like a standard electrode. So like we mentioned, right, we typically picked a metal, right? So obviously the metal is hooked up to the corresponding metal. But we can look at a few scenarios. So for example, this iodine reaction here. So if you wanted to do this reaction, there's no metal, right? You can't really like hook it to the iodine crystals. That will not work. So iodine will just dissolve in solution. So if you were trying to use, you know, this half reaction, or what's another one that just has a bunch of ions like this one, this manganese one, right? There's no solid manganese involved here. And so in those types of redox reactions, so it mentions, right, we run into an ion or different oxidation state or again a gas, then we need to use an inert electrode and graphite. So that's where the pencils came in handy from lab last time. But like we mentioned, there could also be platinum electrodes or glassy carbon. So yeah, looking at your homework, you have some platinum electrodes to help. Trying to see if there's anything. And so again, right, they don't participate in the reaction, but they just provide a surface for those electrons to transfer. And so then if we are using an inert electrode, so we can see the difference. So now we can look at this cell here. We might want to calculate our cell potential as well. But let's just look at kind of the outline and showing us how to build this cell. So again, right, our anode is on our left side always. So there's our iron, so of course, right, iron metal. And then yes, notice how in this one they just put iron 2+, right? Doesn't matter. So iron nitrate obviously would be a good choice, but iron chloride would also work, iron sulfate, whatever, just as long as it's in the 2+ oxidation state. Then we have our little bridge here indicating our separate cell. And then, right, it's telling us this is that manganese one that I actually happened to mention. And so we can see that everything is aqueous. So, okay, that doesn't really work out, right? So that's kind of an indication that we're going to need some sort of electrode there. And so, yes, they've indicated it. And again, right, the single line to show us that this is our electrode then. And now we can see that translated in the diagram. And so you can see our alligator clip hooked up to our surface, obviously, right, dipped in our liquid here. Again, just so we have a transfer of electrons, right? We just need a surface for that to occur in. So before we take our break, let's see if we can calculate then what's the potential, our cell potential then. So our voltage. So see if you can look up our redox potential for the oxidation side, the reduction side, and so then what's our expected cell potential. So what do we find, what was our reduction potential for iron? So we're looking for iron 2 to 0. So I think it's down here. So it looks like, so negative 0.45, but of course, let's flip it. So iron gives us iron 2 plus 2 electrons, so that's positive 0.45 volts now. And so now let's look at our reduction side. So that manganese one is somewhere at the top. Just trying to make sure I picked the correct one. Is that the correct one? No, I think I picked the wrong one. So MnO4, so this one, right? No, this one, sorry. Just making sure I picked the correct one. So we got this one, right? The 1.51 volts. So those are always tricky, right? So just make sure you're picking the ones in the correct oxidation states. So it just gave us these and then some acid. So 1.54 volts or 51. And, oh, I should have realized the reaction was up there. And so what do we get when we add these together? What's our cell potential?
Oh wait, is that positive 40.45?
Yeah, positive. So then 1 point.
Is it positive because we have to switch it?
Yeah, because it started off, right, as negative, but then we switched it. So then what's our final?
1.96.
So 1.96 volts there. So that looks good. All right, so let's take our little break, so a 10-minute break. Oh yeah, and don't forget, I think they still have pizza going on downstairs.
What about copies of the solar reduction potential?
Oh, you need, yeah, I'll get some more copies. All right, let's continue, if we all made it back from break time. And so again, I think this is kind of review. I have one more standard reduction potential sheet, I think. If people wanted an extra copy, otherwise I can make some more. But like we had mentioned, also this is kind of an aside, but we should. So if you ever get bored or want to like look more into this and kind of what makes a good like redox material, this is a really, really, really good paper. So maybe I'll post a link to it. But this is actually on the Journal of Chemical Education, so y'all should have access to it, but I think it might be open access anyways because this paper has become really important in what's called cyclic voltammetry. And so that just is how you measure the redox potential essentially. And so Gillian Dempsey has become a really famous professor because of this. She's at UNC Chapel Hill. Ironically, she was only hired as a dual hire with her husband, but then she ended up being the better hire, ironically. Anyways, so kind of the long and the short of this, and what I was trying to get at with some of the things that we say, is you want it to be what's called reversible. And so this is they call it a duck because it kind of looks like a duck. You can tell, right? They put the little bill there. But this is like a nice graph, essentially. So this is what you want it to look like. And kind of scrolling down, I was trying to find a better picture. And so, right, you can basically measure your oxidation and reduction potentials, so where it lands on the graph, so how high and low it is obviously corresponds to its potential. But then part of this is you want to run what's called a CV. So you run this CV for a while, and the whole point is that you want it to keep this nice duck shape. And so if the duck falls apart, then that means something is going on, right? So it could be a side reaction, maybe your electrode's just getting dirty, worst case scenario. But yeah, it usually indicates that your material is kind of breaking down and not stable. So then, right, that's obviously not a good material for like a battery, especially if you're talking about trying to make a nice reversible battery. And so like I said, I'll post a link to that. It gets, a little deeper though into some of these things. And so part of that and what that paper probably mentions is that again, you have to have some sort of potential to compare it to. So like I said, we covered this last time, but we're kind of going through it again. And if you look at other papers, so if we pull that one back up, oops, that's not the paper. So when we read our standard reduction potential charts, so we've mentioned that our hydrogen reaction was assigned to 0. So that's obviously used as a standard. But then what chemists use, because again, right, I mean, you got to find something that you can throw in with your substance. And so this little thing is ferrocene. So this means, and this is very common for inorganic chemistry, is then you compare your compounds all to the reduction potential of ferrocene. So sometimes they're reported relative to ferrocene, sometimes relative then to hydrogen. You just recalculate. But basically, you can literally throw in a little bit of ferrocene, and then you can run it with your compound, so then you see your ferrocene, your compound, and then you can get the correct voltage, right? So again, you always have to have some standard. And ferrocene's a fun compound. So this is ferrocene, just so you know what we're talking about. And it's a nice orange powder, commercially available, so you can also make it, but. All right, so back to standard hydrogen potential. So again, right in this case, we've just assigned this reduction potential to be 0. So that's our standard hydrogen electrode. And again, right, what all these values are based off of. And so same thing, right? So ferrocene would be referenced to the hydrogen, and then you can reference your compound of ferrocene. And so as long as you always have a reference, everything is good. And so again, just trying to appreciate these trends. So half reactions with a stronger tendency towards reduction than the standard hydrogen electrode have a positive value. And so, right, we're just comparing, oops, I lost hydrogen again. So hydrogen, so right, more positive value. And then versus, so half reactions with a stronger tendency towards oxidation have negative values. And then again, right, we've looked at this, so obviously, right, we flip the sign as we flip the equation. So I always find that, again, the simplest thing to do is which way is your reaction going, and then add it. And so again, right, we're just appreciating our potential energy here, so looking at our anode. And so this is why I don't like this format. So right, we have our anode, but I like flipping our sign so it's clear what's going on here. So I don't like that they didn't flip the sign. So kind of watch for that. They might just report it as such. And again, right, so we've kind of already seen this when we connect our half cells. Obviously, the electrons are going to flow so that the reaction, the half reaction with a stronger tendency will occur. Again, just looking for that positive voltage overall. And so kind of with this, which way, right, will the electrons flow? So they have, again, right, these little tricks. Of course, it's going from the anode to the cathode, and then we're comparing, again, these oxidation potentials. So although this is kind of confusing because now they're giving it to us in our oxidation potentials, which is why I always say, right, just flip your reactions so you're not confused. So once we flip them, okay, well I can tell zinc, right, is acting as my anode, at least how it's written. This doesn't work out, obviously, right, because our half reactions don't add. So flip that. And now we get positive 0.34 volts. And again, right, just re-emphasizing that yes, it is positive, and this is the correct direction, right? It's going to be flowing from zinc to copper. So zinc is the anode. And then obviously, right, if you flip it, it's nothing to get too worried about, right? We can just see, okay, well, if we had tried it the reverse way, so if copper is supplying the electrons, let's see what that is. So then, right, negative 0.34 volts. And if copper is acting as my anode, then, right, zinc would have to be the cathode. So then we write that reaction in the correct form for the role it would be playing, flip the sign. So that would be negative 0.76 volts. So right now we can tell this cell, at least right, set up as such, where we're trying to act like the copper is our anode. So we see that it has a negative potential, right? And so all we're saying is like electrons will not flow this way. So electrons will not flow, right, from copper to zinc essentially. So that's all we're really establishing. So we add it up, right? You see it's negative. You know it's just not going to go in that direction. And then, right, the question is, well, is it going to go in the other direction? Probably, right? So you just set up the cell, and then the electrons will just be flowing from zinc to copper instead. And like I mentioned, right, if your voltmeter, if you were to do this, your voltmeter reads negative, then you probably just have your signs, your little electrodes flipped. So you're just measuring, right, the wrong way the electrons are flowing. And then again, if we have a completely non-spontaneous process, then like we mentioned with the electrolysis, we can apply voltage and get it to occur. And this is again, right, just our recap. And so we've seen that again, right, with this negative reduction potential, that we have our stronger reducing agents on the bottom. And so again, right, orient yourselves kind of reaction-wise. Like, yes, right, these are very reactive. So they always lose one electron, so that makes sense that they want to supply your electrons, right? And obviously this is not a favorable reaction, so that takes a pretty high voltage. So going back to, right, metal mining production and what has to go into it, both energy and chemically wise. And so again, right, if you're a chemist too, just like thinking about how you want to do a reaction. So obviously, like sodium and potassium and lithium are used a lot as reducing agents, but sometimes, right, they're too strong. And I always joke, right, it's like a bomb went off then if your reduction potential is a little bit too much. Again, there's a lot of little nuances to chemistry too. And then, of course, as we go to the upper end of this chart, right, we have fluorine, oxidizing agents. Fluorine tends to be pretty reactive, And then obviously oxygen's pretty up there as well. Same thing with these permanganates, they tend to be oxidizing agents. So you'll get to that in like CHEM, where these manganese solutions tend to oxidize bonds and add oxygen. So it makes sense that they would be at the top there. So again, just looking at these trends. And then, so we've been doing a pretty good job of this. So again, right, we're just also trying to predict the direction in which our cell's going to flow, or our electrons are going to flow. And so again, they have this kind of trick. I find the tricks kind of confusing. I prefer just adding up the numbers. But again, you can kind of use these trends. So a spontaneous reaction will take place when a reduction half reaction is paired with an oxidation half reaction that is lower on the periodic table. And then if it's the other way, then the reverse reaction is spontaneous. But again, I'll just add, right, check the math. So again, all these statements can be kind of confusing, but you can always just double check the math, right? Check which way it's going, and that will just verify. And so, of course, we mentioned when our E cell, when our potential is positive, then it's spontaneous. Don't forget that, of course, that means delta G will be negative. And then if our cell potential is negative, then that means it's non-spontaneous, and delta G will be positive. Sorry, typo. Same typo. So we've looked at that. So I feel like we're pretty good on this one. Although we could look at this little saying, right? So it's saying, oh, a reduction reaction is paired with an oxidation reaction. So oxidation at the anode, right? So zinc is lower, but again, I find it much easier just to calculate the math on it. All right, so now we start getting into the little differences in this chapter. And so now we'll look at our cell potential. And so cell potentials are intensive properties of matter. And so because our cell potentials are intensive properties, we do not multiply the half cell reactions. So I don't know if you've kind of noticed that, right? So when we're just calculating our potentials, it doesn't matter how many electrons, right, are flowing. We're just looking at our half cell values. And then, so this is where I mentioned, right, they have like different formulas. But again, I get confused by these formulas, and I just prefer to add our half reactions. And I'll say with correct sign. And so, right, this is like for not flipping the sign, but again, I will get confused personally. But you may see this formula. You can use this formula, but again, I will always add the half reactions and flip the sign appropriately. Otherwise, I will get confused myself. All right, so let's just practice then with the standard cell. So we haven't done anything too different yet. All right, so see if you can look up those half cell values and determine our cell potential. So for this one, we just had to find our reactions again. And so it looks like aluminum's down here. And again, right, I'm going to go ahead and flip the sign appropriately. So 1.66. So going back to here, right, I'm going to write the correct half reaction. So we're looking at aluminum going to aluminum 3 plus then, plus 3 electrons. So then that gives me a positive 1.66 volts for that. And then, so trying to find, so now we got to find this nitrate and NO reaction. And if you have the potential, you can yell it at me too. So I think it's this one, right? So we have nitrate in acidic conditions, gives me NO, so it should be that one, 0.96. Oops. And so again, I'll just write out our half reaction. And how many electrons were involved. Lost it again. So 3 electrons, right? So that's where, again, it doesn't matter, although they are both 3, but we don't need to take that into account. And then positive 0.96 volts. And so what do we get for our total cell potential? So 2.62 volts. That sounds good. And again, right, we could compare this to the formula. So first, right, you kind of maybe have to understand that the aluminum is acting as the anode, and then you can take the cathode. So 0.96 minus a minus 1.66. So we would get the same thing with this formula, but like I said, I would drive myself squirrely and be confused on the signs at all times. So I prefer it this way. Again, you're more than welcome to just plug it in to the formula if you're totally comfortable with that. All right, so again, we've kind of belabored this point now a lot. So we're saying, obviously, again, we calculate our positive cell potential, and then our delta G is going to be spontaneous and negative. And so now, see if you can predict which one of these is spontaneous or not, again, as written. And I know it says without calculating the E cell potential, but I will say, like, feel free to. And so again, right, you can just try to base it off of the trends and which one's lower. But I always prefer plugging in the numbers. So how's our problem going? Let's at least look at A. So did we calculate our reduction potential yet of this?
Is it negative 2.82 for the first?
I'm not sure I got 2.82, but I did get a negative number. And so that makes sense, right? And so before we kind of punch in the numbers, we can try to again solve it without calculating our E cell. And so kind of, right, thinking through this. So who's acting as our anode, right? So iron is supposed to be our anode here, except if we compare, so iron, and we have, let's see, iron 2 plus, so where is that? So iron 2 plus versus magnesium. So magnesium's lower, right? So that's already a bad indication that this is spontaneous, right? Because we want the one that's lower to be the anode. But let's plug in the numbers, because again, I find that a lot more straightforward. So going back to this, so writing down our half reactions. So iron solid to iron 2 plus is, so that would be positive 0.45. And then now, so magnesium 2 plus. So this would be in the correct direction. So that's negative 2.37. So that's not good. So magnesium 2 plus to magnesium solid. So negative 2.37. And so we add these up. And so I got like negative 1.92 or so. So we got that now. And so again, right, not good, not spontaneous. Obviously, right, this would just tell us that if we would set up this cell in this way, that it would actually flow from the other direction, right? So from magnesium to iron. So it would be not spontaneous in this direction, though. And so let's look at B. And again, we can try to just do it without the math first. So we're looking at iron and lead. And so again, iron is acting as our anode, at least how this is written. We'll see if that's appropriate. And so it does appear that iron is lower than lead. So that's at least, right, somewhat promising. But again, I like to do the math. And so we have the same reaction, at least. So iron solid to iron 2 plus. So that was, again, positive 0.45. And then let's look up the lead. So lead 2 plus. So that's negative 0.13. So lead 2 plus. Lead solid. Oops. Then 0.45 plus a negative 0.13. And so very small, but still positive, right? 0.32 volts roughly on that one. So yes, this would be spontaneous as written. Again, would not get a lot of juice from that reaction, but. Questions on those? And then, of course, the rest of this question did ask us to kind of draw our cells, so we could at least practice that for B then. So B was the correct one. And just kind of remember your parts of your cell. So, right, I'm not an artist, but just make it simple, right? You got your two beakers there. So iron, right, is our anode, so it should go on the left. And, right, just put some sort of iron 2+ in there. Same thing, right, lead 2+. Then don't forget all the other pieces. So your salt bridge, and then some sort of wire hooking it up to a happy light bulb or something. And then probably want to show the flow of electrons. So at least, so we know that this is the anode, so they're going to flow from iron to our lead there. So that's at least, right, kind of our crude picture and what we need. Again, our electrodes, so don't forget a glassy carbon electrode, again, if we didn't have a metal there. Oh, questions on this? Sorry, I should have made sure everybody drew this out. So yeah, you'll definitely have to draw one of these on your final exam. Although, like I said, your final exam will be take home, so. All right, so then we have our metals dissolving in acid. And so this is, again, kind of going back to your activity series that you did. So you can look back at that lab. And so like we discovered, some metals dissolve in acids. And so, okay, what drives this then? So if the reduction of hydrogen is easier than the reduction of their metal, and so if their ion reduction reaction lies below our H+ reduction on the table. And so let's look at that. And so let's kind of compare from what we remember. So, right, if we're looking at zinc, so zinc did dissolve in acid. And so, right, it's below it. So that makes sense. And then let's find, so if we look at copper, so remember copper was one of the few metals that did not dissolve in acid, but it is above this H2 here. So that does, right, kind of follow along with the reduction potentials and again, right, what you observed. And then all the other ones we expected to dissolve in acid, although, right, I think some of them were pretty slow. Like, I don't know if you saw much with the lead or the tin in the acid, but eventually it should have dissolved. And then, so nitric acid is also used. And so almost all metals then dissolve with nitric acid, so a little bit stronger. And, right, mentions the, obviously the chemistry behind that, that you have the nitrogen now reduced rather than the hydrogen. And so now gold and platinum dissolve in a special combination. So this is aqua regia here. And it's a 3-to-1 HCl to nitric acid solution. And so that dissolves pretty much anything. So if you, I don't know if you remember, there's that story, right, of, now I forgot who won the Nobel Prize, but back when like the Nazis were coming around, he dissolved his gold medal in aqua regia so that they wouldn't take it, and it was just an orange solution. And then don't forget safety on aqua regia. So, right, he was able to store it because it was just like gold in aqua regia, but you really don't want to store it. So aqua regia is just something that you freshly make, and it's, like I said, so it dissolves metals here, obviously, but if it dissolves metals, that means it's a pretty strong oxidant, so got to be careful. So you kind of use this kind of at the end, the last resort to clean things that maybe have metal contaminants. And then, like I said, you don't want to store it because this mixture could become explosive over time. So that's why you don't store it. But yeah, if you ever want to make some gold compounds though, so gold compounds are obviously very expensive, and it's actually economical to buy like literal gold bars and then you dissolve them and kill them. It's the saddest thing ever. I've personally witnessed it. Anyways. All right, so back to this. So I think, like I said, we kind of touched on it in chapter 24, but it's obviously back. We're going to do a few more calculations. And so we have this nice little diagram here kind of showing us the relationship between all these things. So we've been talking about all of them, and so of course now they're just coming together. And so let's again just reflect on what this is saying. So of course, right, if we're looking at a spontaneous reaction, we're just looking at the forward direction formally. And so again, that means that our Gibbs free energy is less than 1. So again, right, we're just saying there's energy available. Our cell potential then is going to be greater than 1 or positive. And then don't forget, right, what your K means as well. So right, K, there's a few things to keep in mind, right, with K, because I think people were confounding a few things as well, right? So remember, K is just any equilibrium expression. And so in this case, right, we're talking about that this is going to favor the product. So all we're saying is, so if our K is greater than 1, right, our products over reactants, so right, we're just saying that there's probably going to be more products than reactants. So again, right, it's going in the forward direction. But what you don't want to confuse it with is Q, right? So remember, Q is just your snapshot in a moment of time, right? And so that's where it can maybe get confusing, right? If Q is greater than K, then it's going to be going reverse. But just kind of keep that separate in your mind, right? Whether we're talking about K, whether we're talking about, right, whether the reactants or products are favored, or are we comparing Q to K? And then, so as you can tell, where we're going in this chapter is just continuing to relate all these variables. So I believe we had introduced this formula in chapter 24, and it might have come up on your exam maybe. And so, right, we have our delta G equals our negative RT times our natural log of K. And remember, right, R is just 8.314 for our joules. So that's, right, our energy calculation there. So remember, Gibbs is energy. And so K, right, our K is just telling us, again, which way our equilibrium lies. And so now we want to add in here, well, how do we relate this to our cell potential now? And so we have our equation here. So our Gibbs free energy then is equal to negative NFE here. And so N, this is where we have to account, right, for the number of moles of the electrons. And so, right, like how many are being transferred. So we'll have to, again, pay attention, right, to how many electrons are involved in each process. And then Faraday's constant just brings us to a molar amount. So, right, so now we're in moles of electrons. And then E is, of course, our E cell potential. And then we have this additional formula. So we'll look at this. So our E cell then is equal to 0.0592 volts over N. So again, right, N would be our number of electrons times our log of K. So this is really, right, kind of combining these two formulas then to give us this form. So depending, right, what we want to compare to, if we're trying to go from our E cell to our Gibbs, or trying to go from our equilibrium value to our E cell. So we have all these relationships. All right, so now let's try to work through this one. And so at least start with, right, your cell potential. So we have this reaction, iodine plus bromine gives us iodide and bromine liquid out. And so we want to figure out, right, is it spontaneous under standard conditions? And we want to calculate our delta G. So like I said, just try to start with your cell potential at least. Otherwise, you can try to plug it into there. And so what do we get for our cell potentials? So negative 0.55 volts, so that sounds correct. So hang on, help me. So what'd you get for the potential for the bromine one? So 1.09, and then the iodine one, 0.54 volts. Excellent. So did everybody get that at least? And so, right, this already looks bad for the spontaneous, I mean, since it's negative. But they did ask us to calculate our delta G. So let's go ahead and do that, right, with this formula. And so this is where the electrons comes into play. So, right, we have 2 electrons being transferred on each side. So then that corresponds to our N here. So N is 2. And so now we can plug in the rest of the values. So delta G equals negative N Fe. So equals negative 2 times, so Faraday's constant, 96,485 coulombs, times our negative 0.55 volts or joules per coulomb. And anyone have a number while I punch it in? Did you multiply it by Faraday's constant? And then it should be positive because we had a negative cell potential, and then our formula is negative. So I got negative like 106,000 joules. Is that what other people?
Yeah, I got 10,000 too, but I timed it by 54 and 55.
Oh, okay, so pretty close. So, right, could be some rounding discrepancies. So, yeah, about 106,000 roughly joules then. And again, the important part is that it's positive, so non-spontaneous, of course, which, again, like I said, right, we were already expecting that from our negative cell potential. All right, so we'll pick that up on Thursday. So we'll keep doing some more calculations, and all we have left is kind of the Nernst equation and some concentration issues there. So we'll do some more practice problems. Otherwise, I will see y'all in lab, or see y'all on Thursday. And I'll post the notes. Oh, sweet, yeah.
Just right there?
Yep.